controlling hydrocarbon transport and electron beam-induced deposition on single-layer graphene, toward atomic scale synthesis in the scanning transmission electron microscope. This manuscript was featured on the cover of the journal Nano Select in 2022. One of our primary research goals is to pioneer the development of atomically precise fabrication technology to enable manufacturing at the atomic scale. This ability will have a significant impact on the technological development of future devices and will enhance the fundamental understanding of atomic processes generally. However, a continual challenge in working with materials, and in particular with graphene, at the scale of single atoms is that of cleanliness. Graphene is ubiquitously dirty. However, in situ thermal cleaning procedures have shown promise for cleaning away surface residue. Nevertheless, hydrocarbon deposition can still be a problem. In this work, we illustrate a simple method for maintaining clean graphene at elevated temperatures. Here's a brief summary of the problem. When examining a nice graphene sample in the microscope, you will typically see something like this. The brighter areas are contaminants adhered to the graphene surface. Only the very small dark patches are clean graphene. By heating the graphene in situ, you can clean off a majority of the fixed surface contaminants and create much larger clean patches. However, often when you zoom in, you will observe hydrocarbon deposition. Here, the little boxed patch was initially clean graphene, and upon exposure to the more concentrated E-beam caused by zooming into the central region, a square deposit was formed on the surface. This completely obscures the graphene and clearly prevents further inquiry into the atomic dynamics. We would like a method to prevent this, so we need a deeper understanding of the hydrocarbon deposition process. To this end, we examined a graphene sample that was heated to 900 degrees centigrade. We first examined these two regions. In region 1, we acquired a video for 42 seconds. Here it is, sped up. We see that there is hydrocarbon growth along the edges of the visible surface contamination, as well as nucleation of new growth sites in the pristine regions. Now, we compare this with a similar video obtained in region 2. This one was acquired for 83 seconds. What we observe is that this hydrocarbon growth is occurring only on one side of this barrier. The main difference between the two sides is that the area with no growth is completely encircled by a ring of fixed surface contaminants, while the side that exhibits growth is not encircled. It is, of course, not a foregone conclusion that this is the explanation. We need a way to demonstrate this hypothesis conclusively. So, we performed a slight revision to the experiment. First, we deposited a wall in region 1 that now seals off a portion of the graphene that was previously open. Acquiring a new video across this wall, we observe that deposition only occurs on the outside. If we go back to region 2, we find that we no longer get deposition on either side of the wall. These are fairly small areas. Let's try a larger area. This blue region was almost fully enclosed. We deposited a barrier across the opening at the top, and then took another video across the barrier. Again, we see deposition on the outside, but no longer any on the inside. In this way, the graphene within the corralled region can be imaged with high resolution at elevated temperatures. We performed experiments for several days within this corralled region without any further hydrocarbon deposition, so it does not appear to be simply a temporary fix, like a beam shower. Indeed, if we look at the deposition rate through time, we observe a marked decrease over the course of these experiments, which suggests that the precursor hydrocarbons are desorbing, and eventually the deposition would stop if we were patient enough. To reinforce these observations from a theoretical perspective, we developed a 2D reaction diffusion model that was able to quantitatively replicate the observed deposition rates. Many of the governing parameters of this model are unknown, so we simply selected reasonable estimates, and then fit the model to the data using the precursor surface diffusion coefficient and the equilibrium precursor surface concentration as fitting parameters. At the current state, the effects of these two parameters cannot be disentangled. Nevertheless, it is instructive that a two-dimensional reaction-diffusion model is able to capture the data. All the evidence points to the idea that these hydrocarbons are confined to diffuse along the graphene surface, which means that a simple physical barrier is sufficient to block their ingress and preserve the graphene cleanliness at elevated temperatures. This understanding will be critical for the further development of atomic fabrication techniques and the building of functionalized atomic devices. Links to the publication can be found in the comment section below.